All right, hello everyone. My name is Larry Kidder. I'm here from the SXS collaboration, telling you about SpECTRE, a new code that our collaboration is developing to do relativistic astrophysics. So the goals of SpECTRE are to do higher accuracy simulations for solving problems in relativistic astrophysics, primarily targeted toward gravitational wave observations, either compact binaries or core class. We want to make efficient use of exascale computers, and unlike our previous code SpEC, which is closed source, we want this to be an open source community code that's anyone can use. So our code is currently open source. It's on GitHub, and all development is done on this open source GitHub page. There are no secret branches or anything, so you can go browse our history whenever you want. Before I get started about SpECTRE, I want to just remind you about the success of the spectral Einstein code. This code is now almost 20 years old. This was developed primarily by myself, Mark Shiel and Harold Pfeiffer at Cornell and Caltech in the early 2000s. And we've had a lot of collaborators join us after that. With this, we've built a large waveform of gravitational wave, catalog of gravitational waveforms, primarily for binary black hole systems. We also have a few neutron star binary waveforms, but not as many as some other waveforms. On the bottom, I'm showing you a grid. So we use high order spectral methods on a collection of spherical shells and cylinders and cubes, which have black holes X-size. And this is the grid frame where we keep everything fixed, the structure of the grid fixed. And then we use coordinate mappings to distort and rotate and follow the black hole's motions. And this is done by tracking where the horizons move and using a control system to adjust these maps. So on the right side, this is what the black holes would look like in the inner frame. So the power of spectral methods is they exponentially converge for smooth problems. So they're ideally situated for binary black hole problems. Typical simulations for SpEC utilize only 60 to 90 cores, which on now a modern computer is now 1/2 to 2 nodes of a computer. When we started, there were only 2 cores per node, so we had to use nodes. The typical amount of time to do a simulation of around 32 orbits for various mass ratios and spins I've listed here in terms of expanse kilo-CPU hours. So for all of these systems are rather extreme in either the spins or the mass ratios. For low mass, low spin systems, the amount of time needed is on the order of about 10,000 CPU hours to do the full 32 orbit simulation. So we'd like to attack problems with matter using high order methods whenever possible. Of course, spectral methods break down when you have shocks and so on, so you'd never be able to get high order convergence in the region of shock and surfaces. In such cases, what SpEC does to do its neutron star simulations is it does its hydrodynamics on a finite difference grid. So in SpECTRE, what we wanted to do was explore an option which is known as a discontinuous Galerkin method, which is sort of a hybrid between spectral methods and finite difference methods. So the basic idea of a discontinuous Galerkin method is you have your solution standard and you break it up into set of 3 cells here on this grid. And in each cell, you approximate the solution as some function of a known analytic function, a series expansion in terms of analytic functions. And you allow the solution to be discontinuous at boundaries, and you then communicate, in order for information to propagate across the grid, you have to communicate fluxes between neighboring elements. Discontinuous Galerkin methods are essentially equivalent to spectral methods for smooth problems, that you get the same exponential convergence. But when you have shocks and such things, you need to apply some techniques called slope limiters, which sort of handle the shocks by limiting large slopes in the solution. Now, there are a number of these slope limiters that were in the mathematical physics literature, and we tried a wide variety of them. And while you can tune a particular slope limiter to a particular test problem, they're not very robust when you try to apply them generically to any type of given problem. So here's an example where we applied limiters and did a discontinuous Galerkin MHD simulation of a cylindrical blast wave. And if anyone knows what the result of the cylindrical blast wave should be, this looks like crack. And so you can tune certain parameters in these limiters to get the solution well, but if then you use these parameters to try to do a different problem, say Kelvin-Helmholtz instability, you'll find that the solution is garbage in that case. So one of our grad students at the time, who's now our faculty member at new faculty at Cornell, he was here, did his PhD thesis, and a large section of it focused on developing a method that combined discontinuous Galerkin and finite difference, where basically you switch between when the discontinuous Galerkin method fails, you switch that cell to a finite difference method. And so the way it's done is, say you have a discontinuous DG cell with 6 grid points, you would then switch to a finite difference method within that cell that has 2n-1 grid points if you have n DG grid points. And then there's a series of troubled cell indicators that you can apply to determine when you should switch back and forth between the DG method and the finite difference method. And so basically, the method is you take a DG step, you see whether the DG solution is valid. If it is, you just keep doing DG steps in that cell. If it's not, you retake this time step using a finite difference method. And while you're taking finite difference method steps, you conversely check to see whether you can go back to your DG grid. And so they're the same test problem now again, where now we see what we expect to see for the cylindrical blast wave. And this is shown for 2 resolutions, where we've changed both the order of the DG cell from 3rd order has a 4.6 order. No, 3rd order, 3.6 cell. All right. And one of the things on this visualization is you see a bunch of little cubes here. This is actually a visualization artifact because the DG points are on each cell include points on the boundary, so you can smoothly visualize it. Whereas the finite difference cells inside a DG element are cell-centered. So there's a little square which will only show up when that cell is doing finite difference. So it's a good way of seeing which cells in the simulation are doing finite difference versus DG. Here's another test problem where we do the Helmholtz instability. Again, you see that parts of the flow will be still doing DG where the problem is relatively smooth. And here's the video, which illustrates as a function of time, the code switching from DG to subcell to resolve the vortices, and that some cells then go back to DG when the density becomes smoother in those spots. All right, another test problem we did was we looked at a magnetized neutron star. you can look at the perturbations of the neutron star. These can be compared to the oscillation frequencies of the star. And we see that as we increase the resolution, we can resolve more and more of these oscillation frequencies. And this is just showing how, as we increase the resolution, we converge to keeping the maximum density constant in time. And here's a look inside a rotating neutron star, where you see that most of the interior stays on the DG grid, where subcell is only occurring towards the surface of the star. So besides doing these GRMHD test problems, SpECTRE has produced several other results, one of which is the ability to do Cauchy characteristic extraction, which I'll talk about a little bit more in detail in the next couple slides. SpECTRE also has an elliptic solver, which we've applied to solve thermal noise, a thermal noise problem. We've also been exploring an enthalpy parameterized equation of states. This is work done by a graduate student at Caltech. And a graduate student at AEI has published a paper where he does world tube excision. The motivation for this is if you have an unequal mass binary black hole, it gets very difficult to resolve the much smaller black hole if you need to excise it. So instead of excising it, the idea is to make a little world tube and do some sort of Cauchy evolution of the interior of the smaller black hole. So he's tested this with some scalar wave problems on a curved background. So this is a recently published paper by Nico Wittek, the grad student who led the project. So Cauchy characteristic evolution, if you don't know what that is, you have your binary systems that you evolve on your Cauchy domain. It's a series of time slices, and we want to predict accurately what the gravitational radiation is at null infinity. And so what you do is you feed from a boundary of your Cauchy domain. You have a separate code which does characteristic evolutions. You have to initialize both of these surfaces in order to propagate the waves out to infinity. We've had three generations of CCE codes within SPEC and then SpECTRE. This final one was led by Jordan Moxon, and he got the problem to work right well. And with this, we are actually able to extract the gravitational waves to infinity and capture the memory effects, which we could not capture by doing extrapolation of radiation from our binary black hole simulations in SpEC. So we're able to extract, strain the news and all the file components out to null infinity. And so this has led to a series of papers analyzing memory effects in various binary black hole systems. So some of the features that SpECTRE has right now, we have this DG subcell solver to do generalized GRMHD. We can solve Einstein's equations. We can do binary black hole simulations. There, we don't need the subcell solver. Because the problem is smooth, you can just do DG. We're in the process of adding adaptive mesh refinement. We have the actual mechanisms in that allow us to create new elements, do both H and P refinement, where H refinement says that you split a DG element into multiple parts, or you can adjust the number of points you have in a given DG element. That's called P refinement. And on a branch, I have P refinement working with scalar waves. So getting that in for the full GRMHD system and the generalized harmonic system we use for binary black hole evolutions should be done within a couple months. We have various equations of states, analytic and tabulated. We have support for local time stepping. We're working on IMEX time stepping. It's being tested now. as I mentioned, we have an elliptic solver, and we have various, we want to do neutrino transports. We have the beginnings of M1 coded, but we've not really done any test problems yet. So I just wanted to show a few examples of work in progress. Our binary black hole simulations, they're being pushed primarily by Jeffrey Lovelace at Cal State Fullerton. So this is just equal mass non-spinning black holes. We can do 12 orbits. We're not quite to merger yet. This is a simulation of the video on the right is showing the black holes going around each other and the radiation being emitted. We can compare the accuracy of the SpECTRE to the SpEC waveforms for the leading order waves and show the amplitude and show that we're agreeing with our previous code. Francois Foucault is leading our efforts to push binary neutron star simulations. As of last week, these were dying immediately after starting with the initial data. But just in the last week, we've gone from not being able to do anything to being able to do this, which is an orbit. You'll see in this movie that the neutron stars will eventually touch. And the area in between switches to subcell as the matter flows into that region. We got this far as of 8 p.m. last night. Sometime overnight, we got to this far. So we've merged the first merger of neutron stars within SpECTRE, and the simulation has died because there's some matter in this element that is not set up to do subcell yet. So that's as far as we can go right now, but it's definitely work in progress and making actually faster progress than we expected. So we're very happy with that. We also have a postdoc at Caltech, Michael Pakos, who's working on the core collapse supernova. This is just showing his initial configuration for a rotating neutron star. He's done short simulations, gotten to bounce, but there's just some issues still to be worked out before we're going to get any further with that. And then Yoon-Soo Kim is a graduate student at Caltech. He's doing some simulations of force-free E&M. On the left is a rotating neutron star where the neutron star is excised, where the magnetic field is aligned with the spin axis of rotation. On the right is a test problem, the wall test problem, magnetic fields around the black hole. So a lot of exciting work getting done now in SpECTRE. Towards making this a open source community code, we're going to have a SpECTRE workshop next summer at ICERM. Some dates in early August. There's a link there for the program that you can go to. The schedule hasn't been set. And also another thing I'd like to advertise, if you don't know about it, is that there's a monthly numerical relativity community call where give students or anyone who wants to the opportunity to give short talks and about their work. It's very much here's what I'm working on, not finished products. So it's a good way to meet other people in the numerical relativity community. There are instructions at this wiki about how to sign up if you're not already signed up or don't know about them. And so you can involve also a sign up sheet to volunteer to give talks if you want to give a talk. All right, that's all I have to say. Plenty of time for questions.
Yes, questions. Yeah.
All right, I think I have two questions. One is SpECTRE has a two-letter answer, so we'll ask the second afterwards. So for the binary neutron star that just worked, do you have any idea what the convergence properties are?
No.
Good, that's what I expected.
This is a very low resolution run that Neil was running this desktop, so.
Okay.
It's,
Okay, now for the real question.
it will be improved.
It's about 55 grid points across the star, so it was literally just like, does this not blow up before I have something bigger?
Okay, yeah, that's why I said probably too late.
2 days ago it was blowing up, and then last night it wasn't, so.
Okay, thanks. Now maybe for the real question. For the CCE code that you have,
Yes.
as far as I recall, that one is expected to be usable by other codes that aren't specifically SpECTRE because it's mostly standalone.
Yes.
And there is some documentation for how one would do that.
Yes.
Okay.
There are several tutorials linked from that you should be able to find on if you go to our GitHub, but if you can't, let us know and we'll point you to her.
So I'm hoping to bring Deborah Ferguson over to Cornell for a week in the fall to write in form for the Einstein toolkit to basically dump the data so that SpECTRE CC can survive it.
Okay, and since we are importing Deborah to your UC next year, that should be all good. Great. Thank you.
Exactly. So we'll figure out the logistics of it. She's like, well, let me move there first and then settle down a little bit. Okay, fair enough.
Okay.
But yeah, so that's the plan, is to have that sort of over the next several months.
Great. Thank you.
It's super exciting stuff. So I see that like near discontinuities, you got to break down into like finite difference. So what would be the difference between using this DG subcell method versus just like a super high resolution shot capturing scheme, like something that like a mirror that goes to like 7th order accuracy in spatial reconstruction, and then still does slope limiting.
Right. So I mean, our primary then way we think of it is you do find a difference where you everywhere, but where it's smooth, you switch to DG because it's higher order and more computationally efficient. And so we also, Neil has worked out some on the finite difference side, doing adaptive order finite difference, so we can do higher order finite difference and sort of have a spectrum going from fully DG to high order finite difference to, well, only first order or low order shot capturing methods work at the where the most troubled cells are. Okay. And so we should be able to experiment with, look at the efficiency and so on. So
you still make benefit of the efficiency from DG, even though
Yes.
you have to revert to the finite difference in some regions. Okay.
Yeah, this will depend a little bit on the problem, right? If you have like hydro with shocks everywhere, at some point you're going to be doing finite difference everywhere. But in practice, switching to DG in 1D, you require half the number of grid points to be about 10 times more accurate than finite difference. This is just like a property you can prove analytically, spectral method. So per wavelength. And so this means in 3D, you're about 10 times more accurate, or you're 10 times more accurate while about almost 10 times cheaper. That's a I mean, if you look at the numbers for like the spectral Einstein code, right, it's really, really cheap to do these deviation simulations with spec. And that's just ultimately a property of these spectral type methods. So when they work, they're great. When you have shocks, then how do you deal with it? Okay. And so comparing specifically to like high order finite difference or finite volume methods, it's again just that you can use smaller number of ghost zones if you fall back to finite difference because you say, okay, well, I only need to do 4th order finite difference or finite volume because I know there's a discontinuity somewhere in this cluster of 10 by 10 by 10 grid points. Yeah. And so there's no real reason to do like 7th order finite volume because you know you're at a discontinuity. And then you switch to 6th, 8th, 10th order spectral methods whenever the discontinuity moves away. So it's computationally a significant savings. All the students complain when they can't do DG in most of the domain because that's slow. So it makes quite a difference, actually.
Okay. I have more questions, but
all right, there was one in the chat. Okay. So maybe regarding the oscillation frequencies for the magnetized neutron star, were all the modes linear? Yes.
It's just, this is like the standard frequency that you get when you solve the radial pulsation problem. I haven't done the analytic math, but various different ways I think that right.
And were magnetic modes dominant depending on your field configuration?
So basically at a magnetic field strength of 10⁻16 Gauss, which is large. As Carlos explained, unrealistically large. The ratio of magnetic pressure to fluid pressure is still like 10⁻⁵. The magnetic field in a single isolated sitting there, neutrons are basically irrelevant in terms of perturbing these modes.
All right, if you have no other questions.
Yeah. So. Do we have time? I don't. Okay. So you get like really great local efficiency with DG. You want to go to exascale. Sometimes that doesn't. Those two concepts aren't compatible because you don't have enough work.
Yeah,
So
but this is a genuine struggle even with CPUs in general, right?
Yeah.
And so far from what I've seen, GPUs in terms of big usage from like NASA and everything, they're using second order finite volume, and then there's no AMR, no local time stepping, and just dump, run it on 30,000 GPUs. Who cares how much it costs? And so
Right. I mean,
AMR
why
gives
do you need
5x
exascale,
speed up,
right?
local
I mean,
time stepping gives you 5x speed up. Spectral methods gives you 100x speed up. So I think the key where we want to end up is high order methods with this adaptivity on maybe GPUs.
Yeah.
But it's going to be problem dependent, but for at least the in-spiral and certainly for binary black holes, my current take is I can give up a factor of 1,000 performance by switching to second order finite difference to gain a factor of 2 in speed up by switching to GPUs. This again depends on the problem. If you have hydro everywhere and you need to do second order finite difference or finite volume everywhere, then it's a different story. So I think it depends a little bit on the problem.
Yeah, I guess I would argue like exascale isn't the goal, right? We should solve physics problems.
Right. The efficient part is something that I think is something that we're trying to emphasize, right? Like making sure that you efficiently can use the CPU is already a challenge. Getting data to the floating point units fast enough that you're keeping the floating point units busy is even non-trivial on CPUs, especially when you saw the Einstein equations came up earlier, where Chris has talked about the GPUs and the Einstein equation, and it's just a non-trivial task getting the data to the floating point units fast enough so that you're not completely memory bound all the time. And that's like a very big metric of efficiency. And the advice I've always been given sort of from people who work at Intel, software engineers that work on this is it's much easier to scale an inefficient code than a really, really efficient code. And so the first thing you want to do is make sure you are using your floating point units as much as possible, and then try to scale, because that's when you'll hit your limits. That's not trying to imply that anybody's code is inefficient or is scaling because it's inefficient. It's just this is the advice I've heard over and over again. It's a challenge, and that's really, really hard to do.
Sure. One quick last question. I noticed the only difference between the spec and the SpECTRE. I mean, I think this has really promised to be super efficient, so you can map parameter space, and I think I'm more interested in that than super duper UJazz simulations. But your phase, there's a slight phase difference in the gravitational waveform. Do you understand like which one's better, or is there a difference, or is that just a measure of the numerical accuracy?
So we need to do a more detailed study of expected accuracy. So one thing about SpEC is it's 20 years old, and we did a lot of hand tuning of the domain structure. SpEC uses spheres, cylinders, and distorted cubes, where SpECTRE only uses distorted cubes. And so where you put the domain boundaries of these subdomains of various shapes took a lot of efforts to get right. And we haven't done that yet for SpECTRE. So we need to do a detailed analysis of, this is the global phase error, but where is it being dominated? Is it because we have low resolution in some part of the domain versus another part? And so those are questions we're still exploring.
So it's pretty impressive that since you didn't do that fine tuning,
getting really close. We're very happy that we're as close as we are. And so.
Okay.
there are no questions, let's thank Lawrence.